Let's say we have a circuit. These are just regular wires, but I just drew them large so you can see what's happening. And we said before, a source of EMF, if you have some source of EMF here, the role of the source of EMF is to pump charges, negative charges, from one side to the other side. So you get these negative charges accumulating on the surface on this side, and therefore you have a loss of charge on this side, so you have positive charge on the surface of the wires on this side. And the way the charge is distributed is it's not uniform. So you have more charge here, more density, less density, less density, and then it starts to become negative. And this irregular distribution of the charge, non-uniform distribution of the charge, results in an electric field being created inside the wire. And we had a whole video about that before, so we're not going to go through that again. So this is the situation. The source of EMF will just make a very simplistic model of what the source looks like inside. You imagine you have negative charges, electrons, and there are two forces acting on the electrons. One is the electric field, the force due to the electric field, because the positive and negative charges, there'll be an electric field going from the left to the right. And then there are some other force. This other force is due to the battery, due to the source of EMF. And of course, there are different kinds of sources of EMF. You could have chemical batteries, you could have a conveyor belt like a Van de Graaff generator. There are many kinds of sources of EMF. This is supposed to just represent a simplistic idea of how things work. So imagine you have a charge that starts out at some position, and then the energy of the charge field system in this, when the charge is located at this position, is called U initial, small u initial. And then wait for a small amount of time later. Well, this external force, this force that's due to the battery, it's trying to move the charge opposite the way it wants to go. The negative charge, if you let go of it, it'll just go to the left. But because the battery has some way of applying a force on the charge to make it go in the opposite direction it wants to go in, so there's some force applied to the right to force it to go to the right. And so the charge will move some distance delta x, and in that case the energy of the charge field system will be larger. The potential energy will be larger of this charge of this charge field system will be larger when the charge is at this position. So the difference in energy then of the system will be the charge times the potential difference between the 2 points. The charge is minus E, and the potential difference, the potential here is smaller than the potential here, because the electric field goes from high to low, so this point is at a lower potential than this one. So that's why, let's assume it's uniform electric field, so we can say it's minus E times the position, the displacement. Now, what if you want to get the change in energy due to the motion of all the charges in this region? Because there's not just one charge that's moving, there are n charges. And so you can imagine each one of the charges is moving a certain distance. The distance that each charge moves doesn't have to be the same, but we can think of some average displacement that the charges move through, and we can then say that the change in energy is n times this change in average energy due to the motion of each charge. And that is just the number of charges times the charge of each charge times the potential difference, the average potential difference that the charges move through. And this average potential difference, we can write it then as minus E times delta x average. So imagine on average, each charge moves an average distance of delta x average. So this is kind of the idea. So each charge is gaining some energy when it moves from the left to the right, and this gives the total amount of energy that the charges have gained in a certain amount of time, delta t. And as you see here, the minus and minus cancel, and you get a positive number, because the amount of energy is getting bigger. The negative charges are going to the right. The potential energy of the system is getting bigger. So this battery is delivering energy to the charge field system. So if we look at the equation a bit more, this n, the number of particles, as we've seen before when we talked about current, you can write it as the number of charges per unit volume times the volume. And the volume is the area times the length, the total length. So that's easy. And then let's now look at the rate at which energy is delivered. So the rate is the change in energy divided by the change in time, the amount of time. So if you look at the previous slide and you divide by delta t, now you have here delta x average by delta t. This is basically the drift speed that the charges move with. On average, we can say that the charges move with some kind of average speed, delta x average by delta t. So we can replace delta x average by delta t by the drift speed. And then we get this equation. So I arranged things in a certain way. It's exactly the same as before, but I just arranged things in a certain way so that you can see how familiar they are. So this is n times the charge times the drift speed. This is what? This is J, and times the area, that gives you the current. This is just the magnitude of the current as a positive number. And this term is just the potential electric field times the total distance is just the potential difference between the terminals of the battery. And all these are positive numbers. So we can write then that the power delivered by the battery, which is the rate at which the battery is delivering energy to the circuit, it's the current times the potential difference. The current times the potential at A minus the potential at B. A has a higher potential than B. And we know from before that the difference in potential is equal to the EMF for at least for an ideal battery, source of EMF. So we can write down also the power delivered by the battery is I times the potential difference across the battery, and it's I times the EMF, assuming this is an ideal battery.